I want you to start off today by doing a little thought experiment with me.
Oh, I love these.
Right. So I want you to think about human communication. And I don't just mean the words we use, but how our actual methods of passing information back and forth have evolved. Because if you really look at it, it evolved entirely out of a shared, almost desperate desire for sheer convenience.
Yeah, humans are fundamentally lazy in the best way possible.
Exactly. We optimize. Just picture the timeline of our history for a second. Imagine you were living centuries ago, and you need to get an urgent message to someone in the next town over, let alone across a continent.
The friction is just incredible.
The friction involved in that simple act is staggering when you actually break it down. You had to sit down, write a physical letter by hand, find a courier, hand it to someone on a literal horse, and then wait days, or maybe even weeks, just for a simple reply.
Yeah, the latency was measured in seasons sometimes.
Right. And we inherently hated that friction. We looked for shortcuts because humans are hardwired to optimize. We needed faster signals. And the source material we're looking at today uses this brilliant visual that really stuck with me.
The castle guards.
Yes. Imagine guards standing on the stone walls of a massive, sprawling medieval castle. Instead of running a mile to relay a message, they literally use synchronized clapping sequences to signal that the king has arrived, or to sound the alarm that an attack is imminent.
Because it cuts through the physical distance instantly?
Exactly. It's instantaneous.
Yeah.
That is a massive leap in convenience and bandwidth compared to the handwritten letter on a horse. But of course, we're never satisfied.
Never.
That clapping evolved into the telegraph, sending electrical pulses over wires, which evolved into wired telephones. But wired phones meant you were tethered to a physical wall in a specific building, which introduced a new kind of friction.
So we invented mobile phones so we could walk around the planet untethered.
Right. And then we realized we wanted all of human knowledge accessible in our pockets, so we integrated the internet. And finally, we wanted to see the person we were talking to without the friction of travel, bringing us to modern, zero-latency, high-definition video calls. Every single step, every technological revolution was driven by us just wanting the transfer of information to be easier and more seamless.
It's a phenomenal way to frame human progress, honestly, looking at it through that lens of reducing friction. And what's crucial to understand about that framing is that this exact same relentless, unyielding drive for human convenience is the fundamental engine that pushed the technology world to evolve.
From traditional machine learning straight into deep learning.
Precisely. From what we usually refer to as ML, straight into the current era of deep learning, or DL. We really have to separate the myth from the reality here.
Yeah, it wasn't just magic.
No, not at all. We didn't make the leap to deep learning just because the underlying mathematics were elegant, or because computer scientists suddenly wanted to do something computationally heavier just for the intellectual thrill of it.
They didn't just wake up and say, hey, let's make this harder.
Exactly. We did it because the old way of doing things became profoundly inconvenient for the humans managing the systems. It hit a hard, unforgiving wall. We reached a point where we desperately needed a system that required less hand-holding, significantly less manual labor, and just less constant human interference.
We wanted the tech to do the heavy lifting.
Right, mirroring that exact same trajectory you just described, from the physical labor of the horse-drawn letter to the invisible, effortless magic of the video call. The evolution of AI architecture is, at its core, a story of outsourcing our own cognitive friction to the machine.
Okay, let's unpack this. Welcome to this deep dive into a really fascinating set of source materials we've compiled for you today, explicitly titled The Evolution and Architecture of Deep Learning.
We have a very clear, very ambitious goal for you today.
We really do. By the time we wrap up this deep dive, you won't just be throwing around the latest tech buzzwords at your next meeting. You are going to fundamentally understand the underlying mechanics of how artificial intelligence actually learns.
You'll understand why it's structured the way it is, the math that drives it, and the architecture that powers the tools you use every single day.
So let's start with the era before deep learning completely took over the landscape. Talk to me about this machine learning wall. Why did the tech industry hit a bottleneck, and why did we so desperately need a paradigm shift?
Well, traditional machine learning was a massive, necessary stepping stone. It laid the statistical and computational foundation for everything we do now. It proved that machines could find patterns.
But there was a catch.
A huge catch. The roadblock wasn't that the machines were inherently flawed. The roadblock was that the models required an unsustainable amount of human effort to set up. It was a technological equivalent of having to manually write that letter and ride the horse yourself before the machine could do its job.
The human was the bottleneck.
Exactly. In traditional ML, the human engineer was the bottleneck because the human had to define the features the machine was supposed to look for.
The source material illustrates this beautifully with what it calls the nightmare of manual rules. And they use an apple as an analogy, which I love.
That's a great analogy.
So if I'm a programmer a decade ago and I want to teach a traditional ML model to recognize an apple in a digital picture, I can't just dump a folder of JPEGs on the computer and say, hey, figure it out.
No, it would have no idea what to do with them.
Right. I have to sit down and explicitly mathematically write out the rigid rules for what constitutes an apple. I have to tell the computer to look for a circular shape. But how do you even define circular in rigid code?
You have to define the mathematical curvature of the pixels.
Which sounds awful. And then you have to say, look for red or green colors, defining the exact hexadecimal ranges for those specific shades. Then you tell it to look for a smooth texture, trying to translate the abstract human concept of smoothness into numerical pixel variance values. It just sounds tedious beyond belief.
That tediousness is exactly why it ceases to be a viable path forward. I mean, manual rule writing becomes a statistical impossibility when you step away from incredibly simple, isolated toy examples like a single apple on a white background and start dealing with massive, complex, real-world data sets.
Like actual text or documents.
Right. Imagine trying to manually write the rules to analyze the emotional sentiment of a 1,000-page legal text or a sprawling novel. How do you write a strict, mathematically rigid rule for sarcasm?
You can't.
You really can't. How do you code a heuristic for irony? Or consider enterprise-level Excel sheets with hundreds of thousands of interconnected variables representing global supply chain logistics, weather patterns, and shifting geopolitical tariffs.
It's just too much data.
A human engineer cannot sit in a cubicle and explicitly program every single interlocking if-then statement required to make sense of that chaotic data. The sheer dimensionality of the complexity completely outpaces human cognitive capacity for manual coding.
And that leads directly into the second huge problem the text highlights, which is struggling with subtleties. Because when you manually write these very strict, rigid rules, the model inherently becomes incredibly brittle.
Very brittle.
The source uses a banana example to show this. Let's say I spent all month writing the perfect manual rules to define a banana. I tell my machine learning model that a banana is defined strictly as yellow and curved. And then I deploy the model.
And it works fine until it doesn't.
Right. What happens when it encounters a green, unripened banana? Or what happens when someone feeds it an image of a rotten brown banana that has gone completely mushy and lost its perfect curve?
The model fails catastrophically.
Because it's too rigid.
Exactly.
Yeah.
It fails because it lacks the capacity for nuance and generalization. Rigid systems simply cannot handle natural variations, and the real world, unlike a controlled laboratory setting, is entirely comprised of natural variations.
The real world is messy.
It's very messy. A traditional ML model doesn't understand the abstract, platonic concept of a banana. It has no semantic understanding. It only understands the strict, inflexible parameters of yellow and curved that you hard-coded into its logic.
So if it's off by even a little bit,
If the real-world data deviates even a fraction of a percent from the manual rules a human provided, the system breaks down. It cannot adapt to the messiness of reality.
which is a huge problem,
Yeah.
because when you combine the absolute nightmare of writing the rules with the fact that the rules break the second things get subtle, you hit the ultimate wall, the scaling problem.
You just can't scale it.
As a human, I can't realistically write manual rules for 100 different types of fruit in a grocery store scanner, let alone try to manually code rules for all the infinite objects, shadows, and weather conditions in a self-driving car's field of vision. It just doesn't scale.
And this highlights the ultimate overarching goal of AI that is explicitly championed in our text: the absolute reduction of human interference.
That's the dream.
It is. The entire driving philosophy of artificial intelligence is to take the cognitive load, the feature engineering, off of us so that humans can focus on more important, higher-level architectural or creative tasks.
Right, because if I'm spending 6 months coding an apple,
Exactly. If a human software engineer has to spend 6 months writing brittle rules for a single piece of fruit, the AI isn't actually saving us time or labor. It's just creating a new, highly specialized type of tedious labor. We desperately needed models that could look at raw data and extract the necessary rules independently.
we needed a system that could learn the essence of an object, the abstract representation of it, without a human ever having to mathematically define its curvature or its color hex codes.
Which brings us to the hero of our story,
Enter deep learning. Deep learning steps onto the stage as the exact technological solution to this scaling problem. It is fundamentally designed to minimize that human input. But to really grasp how it accomplishes this, we have to look at how it consumes information.
The diet of the model, so to speak.
Right. We have to contrast how traditional ML and deep learning handle data. Traditional ML needs its data to be perfectly structured, right?
Yeah, very clean data.
It wants neat, tidy, highly curated Excel tables where everything is labeled, clean, and sorted into clear columns and rows. But deep learning thrives on raw, chaotic data. It wants the raw image pixels, the raw, uncompressed audio waves of someone speaking in a noisy room, the messy, unformatted raw text scraped directly from the internet.
What's fascinating here is the sheer difference in that data appetite and how it directly correlates to long-term performance and scalability.
Tell me more about that.
Well, with traditional machine learning, you eventually hit a hard performance plateau. You can feed an ML model more and more perfectly structured data, but after a certain point, its accuracy flatlines.
It just stops learning.
It doesn't get any smarter, it just stops improving, because its rigid, human-defined rules can only map so much complexity. Deep learning models, on the other hand, possess what the source quite accurately describes as an absolute lust for data.
Lust for data. I love that phrasing.
They are insatiable. The more raw, messy, unstructured data you feed into a deep learning model, the smarter it gets, almost indefinitely. It doesn't hit that same rigid plateau.
Because it's figuring things out itself.
Exactly. It uses all that massive chaotic data to automatically recognize incredibly complex, high-dimensional, nonlinear patterns that traditional ML simply cannot mathematically grasp, because the DL model is dynamically figuring out the rules and features for itself as it consumes the information.
It's the difference between trying to teach a child what a dog is by handing them a spreadsheet of ear lengths and fur color codes versus just letting the child walk through a dog park for an hour.
That's a perfect analogy.
The child figures out the dogness on their own. But of course, there's no free lunch in technology. The source lays out what it calls the ultimate trade-off: interpretability versus performance. It introduces this looming concept of the black box.
This is perhaps the most massive philosophical and technological trade-off that developers and researchers face today. You have to make a conscious choice based on your specific operational needs.
So when do I choose traditional ML?
You choose traditional machine learning if your absolute highest priority is interpretability. This means you operate in an industry where you need to know exactly why the computer made the specific decision it made.
Like finance or healthcare.
Think about highly regulated fields. If you are a financial institution denying someone a mortgage or an insurance company rejecting a claim, by law, you often have to explain the exact parameters that led to that denial. ML allows you to point to the specific human-readable rule that triggered the outcome.
But you lose some performance.
You willingly sacrifice top-tier performance on highly complex data, but you gain complete auditable transparency.
Okay, so what if I don't care why it works? What if I am working on a problem where the only metric of success is that it works perfectly, with the highest possible accuracy?
Then you cross the threshold into deep learning. You choose DL when you demand the absolute best performance and accuracy on incredibly complex, messy data. But you have to find a pact accepting that you are buying into a true black box.
And a black box means?
It means the model will give you a highly accurate, often superhuman answer. But it is extraordinarily difficult and sometimes theoretically impossible to decipher exactly how it arrived at that specific conclusion.
Because the math is just too huge.
The internal calculations are so vast, so deeply layered, and so unimaginably complexly interwoven across millions of parameters that human engineers cannot easily trace the logic path backward. The network figured out its own rules, and those rules operate in a high-dimensional mathematical space that simply might not make intuitive sense to a human mind. It doesn't think like we do.
So bringing this directly to you, the listener, when would you accept a black box in your life? When is it perfectly acceptable to not know how the magic trick worked, as long as the trick is flawless every single time?
We do it every day.
We really do. Think about the real-world deep learning applications pulled straight from our text. Facial recognition on your smartphone. When you glance at your screen to unlock it, you don't care how the phone maps your specific cheekbone structure in milliseconds. You just need it to open instantly and accurately keep strangers out.
Right.
Or distinguishing objects in a split second, like a self-driving car, needing to instantly tell the difference between a tumbling plastic water bottle rolling into the street and a child's toy. You don't need to audit the car's logic. You just need it to hit the brakes for the toy.
Absolutely.
Or powering voice assistants like Gemini, Siri, and Google Assistant. You ask your phone to set a 10-minute pasta timer from across the room. You don't need a mathematical breakdown of how its neural net parsed your localized audio waves against background noise. You just want the timer set. We accept the black box because the convenience and the sheer unmatched performance are simply too good to pass up.
We willingly trade interpretational transparency for unparalleled capability. That is the bargain of the modern tech era.
Yeah.
But even though we refer to it as a black box from the outside regarding its specific decision pathways, we actually have a total granular understanding of the structural architecture of what is happening inside.
We know how the engine is built.
Exactly. We know exactly how the engine is built and how the physics of it operate, even if we can't trace every single microscopic drop of fuel as it burns during a race. And that brings us to the actual physical structure of these systems.
Let's get into the anatomy of a neural network, which the text accurately describes as the literal brains of the deep learning operation. The name itself gives away its inspiration. It is explicitly designed to mimic the biological architecture of the human brain. Let's break down this structural architecture for you.
It's conceptually very beautiful.
A neural network is fundamentally comprised of artificial neurons, usually visualized in diagrams as little circles or nodes, and these neurons are organized into three distinct types of layers. First, you have the input layer.
The sensory organs.
Right. This functions as the sensory organ of the network. This is where you feed the raw data, like the raw numerical pixel values of an image or the text of a document, into the system. Then you move into the hidden layers.
This is where the magic happens.
This is the actual core brain of the operation. This is where all the heavy, complex, high-dimensional calculations happen. There can be dozens, hundreds, or even thousands of these hidden layers stacked on top of each other, which is literally where the word deep and deep learning comes from.
It's referring to the depth of those layers.
Exactly. And finally, you have the output layer. This delivers the final verdict or prediction. The text gives a great concrete example. If you are training a network to classify 10 different types of fruits, your output layer will literally consist of 10 specific neurons, with one dedicated to representing the probability of each specific fruit.
It is an incredibly elegant biomimetic structure. But the actual magic, the capacity for learning, doesn't happen just by having a bunch of isolated neurons sitting there. It happens entirely in how those neurons interact with one another.
The connections.
Right. The neurons in one layer are connected to the neurons in the subsequent layer by mathematical pathways, usually visualized as dense webs of lines connecting the circles in those diagrams. And every single one of these connections, millions or billions of them, has a weight attached to it.
Here's where it gets really interesting, because the underlying concept of weights is the absolute core mechanism of how the network actually learns to value different pieces of information.
A weight is fundamentally a multiplier, a mathematical score. It is the network's internal representation of how important a specific feature or signal is to the final decision it's trying to make.
Let's dwell heavily on the fantastic intuitive example provided in the source material.
The gender guessing one.
Yeah, imagine you have a neural network that is tasked with trying to guess a person's gender based purely on a raw photograph. As the pixel data passes through the complex web of the network, the model has to dynamically decide which structural features of the face are most predictive for its goal.
Through iterative training, the network might independently learn to assign a very heavy, high mathematical weight to features it extracts, like hair length, jaw angularity, or the presence of facial hair.
Because statistically, across its training data, those are strong, reliable indicators.
Exactly. Conversely, it might assign a much lower, almost negligible weight to a feature like general skin texture or eye color, because it learned those specific features are statistically irrelevant to the specific task of determining gender. The weights are the literal manifestation of the network prioritizing and filtering information.
And along with the weights attached to those connections, we have to touch on the bias term. It sounds like a complex statistical concept, but the text explains its function beautifully simply. It's just a small, independent mathematical value added to the mix at the neuron level.
Just a little nudge.
Think of it as a little calibrating nudge. It's a way to fix minor systemic inaccuracies in the calculated weights and ensure the math doesn't skew entirely in one direction. It helps the network shift its baseline guess left or right to better fit the aggregate reality of the data, regardless of the incoming signals.
So we have the static architecture mapped out. We have our layers, our artificial neurons, our interconnected weights, and our biases.
But how does the static blueprint actually wake up and do anything? How does it move from a dumb grid of random numbers to an intelligent system? Let's dive into the learning loop and demystify the actual mechanics of how the model learns from its environment.
This is the crucial transition from passive structure to dynamic action. Training a deep learning model is an incredibly repetitive, iterative process. Boiled down to its essence, it is basically the network making a blind guess, facing the harsh reality that its guess was mathematically wrong, and then systematically adjusting its internal weight so it can be slightly less wrong the next time around.
It's the purest form of trial and error.
It is the purest form of learning, but trial and error, but executed at lightning speed and governed by precise calculus. The very first step of this continuous loop is what we call the forward pass.
The forward pass is the physical act of the network making its prediction. Let's trace this flow so you can really visualize the movement. Data flows strictly sequentially in this phase. It enters the input layer, ripples forward through the massive web of hidden layers, and finally pops out at the output layer as a final numerical guess.
It's a cascade of math.
Let's take our time to spell out the text's specific mathematical example so you can really see it. Imagine three simple inputs flowing in. Let's say the numbers are 0.1, 0.2, and 0.3.
Okay.
And let's pretend the connection weights they encounter are all 10. The network takes the input values and multiplies them by the weights. So 0.1 times 10 is 1, 0.2 times 10 is 2, 0.3 times 10 is 3.
Nice and simple.
Then it aggregates all those results together. 1 plus 2 plus 3 equals 6. Add that little bias nudge at the end, and it passes the result forward. But here's the kicker. Initially, before any training happens, these weights are completely random.
So the guess is terrible.
The first time data does a forward pass, the network's guess is absolute chaotic garbage. It has no idea what it's looking at.
Exactly. The network has made its prediction based on its current, totally random, uncalibrated starting weights. But a guess is entirely useless in a vacuum unless you have a mechanism to know how far off reality you are. So the immediately subsequent step is calculating the error or calculating the loss.
This is where the network faces reality.
Once it outputs its guess at the end of the forward pass, it compares that specific prediction to the actual known reality, the ground truth label of the data you fed it. The numerical divergence between the network's blind guess and the actual reality is quantified as the error.
And the text introduces a very specific, ubiquitous mathematical method to calculate this called mean squared error, or MSE. The term squared is the pivotal part of that equation. Why do we square the error instead of just taking the absolute difference?
It is a vital mathematical trick that shapes the entire learning process. Think about it practically. Let's say the network guesses too high by 5 points on one image, and then on the very next image, it guesses too low by 5 points.
So a +5 and a -5.
Exactly. If you just add the raw linear errors together across a batch, a +5 and a -5 equal exactly 0. The network would look at that aggregate score and falsely assume it has 0 error, tricking itself into thinking it is performing perfectly when it is actually failing wildly on both attempts.
Oh, wow. Yeah, it would just be blind to its own mistakes.
By squaring the error, multiplying the error value by itself, a -5 becomes a +25. Squaring ensures the aggregate error number is always a positive magnitude before you average it out across all the guesses. It completely prevents positive and negative errors from canceling each other out in the math.
But it also punishes big mistakes, right?
Perhaps more importantly, yes. Squaring severely punishes larger mistakes disproportionately. An error of 2 squared is just 4, but an error of 10 squared becomes 100. It forces the network's optimization algorithms to pay urgent, aggressive attention to its most catastrophic failures.
So it's trying to get that error number down to 0.
The ultimate goal, the absolute holy grail for the network during this training phase, is to navigate its mathematical parameters to reach the absolute lowest possible overall error point, a conceptual, multidimensional valley, which is technically known as the local minima.
I love that visual of navigating a topography. You can picture the network like a ball trying to roll down a massive complex hill to reach the absolute lowest point of error at the bottom of the valley. But the network is blind. How does it know which direction is down?
That is the big question.
That brings us to the third and, frankly, most magical step of the loop: backpropagation. I always categorize this in my head as the fixing the mistakes phase. The forward pass went sequentially from input to output. Backpropagation literally runs the network's logic in reverse.
sending signals backward.
The massive error calculation we just determined at the output layer is sent backward through the dense web of hidden layers using complex chain rule calculus. It's essentially sending a hyperspecific feedback signal to every single connection.
It's telling them how to fix it.
Saying, hey, we guessed way too high overall. Weight number 47 in layer 3, your contribution made the error worse. You need to decrease your value slightly. Weight number 12 in layer 1, you helped. You need to increase yours. It meticulously tweaks and adjusts millions or sometimes billions of weights simultaneously so that the next time it encounters that data and does a forward pass, the resulting guess will be fractionally closer to reality.
It is a continuous, relentless cycle.
Mm.
Forward pass to guess, calculate error to measure failure, backpropagate to adjust and learn. But to really understand how this cyclical engine is practically managed by human developers in a lab, we need to decode some insider training terminology.
Let's equip you, the listener, with the lingo.
These are the specific dials and knobs that human engineers still have to tune to keep the engine from exploding or stalling out. Let's rapid fire through the core definitions provided in the source so you are fully equipped to read a research paper. First, dial the epoch.
An epoch is simply defined as one complete, exhausting cycle where the model has looked at absolutely all the data points in your entire training data set exactly once. If you have a training set of 1 million images and the network processes all 1 million of them, updating as it goes, that completes one epoch.
And you usually train models over dozens or hundreds of epochs. Next, we have the concept of batch and batch size.
Because trying to calculate the error and backpropagate across 1 million data points simultaneously takes an astronomical amount of computing power.
It would instantly max out your RAM and crash the system.
So developers break the massive data set down into smaller, highly manageable chunks called batches. The batch size is exactly what it sounds like. It's the number of data points the model processes before it pauses, calculates the average error for that specific chunk, and triggers backpropagation to update its weights.
The text gives a super clear, grounded example. If you have a total of 10,000 data points in your set, and you manually set a batch size of 1,000, you are going to have 10 distinct batches per epoch. The model will pause 10 times during that epoch to update its weights.
And finally, the most delicate dial of all, the learning rate.
This is a tricky one.
The learning rate directly controls the physical size of the mathematical steps the model is allowed to take when tweaking those weights during backpropagation. Remember our visual of the ball rolling down the valley toward the local minima? The learning rate dictates how aggressive those steps down the hill are. If you set the learning rate too high, the network takes massive, reckless leaps. It might entirely jump right over the bottom of the valley, missing the perfect lowest error point and bouncing up the other side, making the model unstable.
But if you go too slow?
If you set the learning rate too small, the network takes microscopic, overly cautious baby steps. It might take 100 years of expensive computing time to finally reach the bottom. It's the ultimate Goldilocks problem for developers, finding the exact rate that dictates how quickly and safely the model reaches that perfect local minima.
It's a delicate balancing act of computational resources versus mathematical stability. So we now understand the sequential flow of data and the calculus of the learning loop, but there is a crucial foundational traffic controller embedded inside this architecture that we haven't discussed yet.
And without it, it all falls apart.
Without it, the entire mathematical house of cards would instantly collapse.
Section 5 of the source material highlights activation functions. I think the best mental model for these is to view them as the mandatory traffic gates of the neural network.
I like that, traffic gates.
Think about the basic arithmetic of the forward pass we just visualized. You multiply weights, add them up, add a bias, and calculate a raw number. But before any artificial neuron is legally allowed to pass its final calculated number forward to the neurons in the next hidden layer, that number is forced to pass through an activation function.
They act as strict gatekeepers. And the expert text tells us they execute two absolutely vital, non-negotiable roles for the network. The first of those vital roles is purely operational standardization.
Why do we need to standardize it?
We desperately need a mechanism to prevent the mathematics from spiraling completely out of control. Remember, a modern deep learning network isn't just 3 inputs and 1 output. It might have hundreds of layers and tens of millions of interconnected neurons.
That's a lot of math.
If you just endlessly keep multiplying inputs by weights and adding them up, layer after layer after layer, without any mathematical constraints, the numbers would exponentially explode. Within just a few layers, you'd be dealing with raw calculations ballooning into the billions or trillions. The computer's memory registers would physically overflow, producing an error, and the training session would instantly crash.
So the gate keeps the numbers manageable.
Activation functions act as a mathematical ceiling and floor, squashing or gating the outputs to keep the numbers contained within a safe, standardized, computable range.
And the second vital role they play is arguably even more conceptually important: nonlinearity. If your network just uses basic sequential multiplication and addition across all its layers, mathematically, the entire massive network just collapses down into one giant, simple linear regression.
It can only ever draw straight lines.
Right. It can only ever draw straight lines to separate data. But the real world, the data we care about, isn't made of straight lines. The text specifically points out that real-world data is infinitely messy, chaotic, and curvy.
Think about human speech waves.
Exactly. Think about the incredibly complex, jagged, overlapping visual of human speech waves recorded on a microphone, or the incredibly intricate, curling, porous structure of a human jawbone in a medical X-ray. A network that can only draw straight mathematical lines can never wrap its logic around that level of complexity.
It needs curves.
Activation functions intentionally introduce curves, bends, and breaks into the math, allowing the network to mold its decision boundaries around incredibly complex, high-dimensional, non-linear problems.
It's what allows the network to actually be deep and learn complex abstractions, rather than just being a massive, expensive linear calculator. The source breaks down the three most ubiquitous types of these gating mechanisms, often referred to as the big three activation functions. Let's start with the one that revolutionized modern training. ReLU.
ReLU, which stands for Rectified Linear Unit. ReLU is the absolute workhorse of modern deep learning. It is primarily used extensively throughout the hidden layers of almost every network. And despite its imposing name, it operates on a staggeringly simple, almost ruthless mathematical rule.
It's a very simple rule.
It looks at the number trying to pass through, and it turns any negative number into a hard zero. That's it.
Yep.
If the neuron's math calculates a positive 5, the ReLU gate stays open and lets a 5 pass through to the next layer. If the math calculates a negative 50 or even a negative 0.1, the ReLU gate slams shut and says, nope, you are now mathematically a 0. Your signal stops here.
It ensures that only positive activating signals pass forward through the network, which ironically makes the network vastly more efficient to compute and solves huge problems with the backpropagation math we used to struggle with.
Then we have the classic sigmoid function.
Sigmoid. Unlike ReLU, you rarely see sigmoid used in the deep hidden layers anymore. It is almost exclusively deployed at the very end of the network, right in the output layer, specifically when you were dealing with binary classification problems.
Because it squashes things.
The sigmoid function takes whatever crazy, unbounded raw number the final neuron calculated, say, 4,500 or negative 800, and it applies an S-shaped mathematical curve that physically squashes that number down into a tiny strict range between exactly 0 and 1.
And the reason we force it between 0 and 1 is because that range is the universal language of probabilities.
Exactly.
If you are asking your trained network a binary question, like, is this a picture of a malignant tumor? You don't want the network's final output to be the raw number 4,000. What is a doctor supposed to do with the number 4,000?
It means nothing in that context.
But if that raw output is forced through a sigmoid gate and it spits out 0.85, you instantly know exactly what that means. The network is mathematically 85% confident it is looking at a tumor.
Generally, anything outputting above 0.5 is treated by the system as a yes or a 1, and anything falling below is a no or a 0. It translates abstract, high-dimensional math into a clean, human-understandable final verdict.
And finally, the text mentions the 10H function. It operates on a very similar curved principle to sigmoid, but instead of squashing the output number strictly between 0 and 1, it stretches the bounds and restricts the final values to sit between -1 and +1.
It mathematically centers the data around an absolute 0, which, depending on the specific statistical distribution of your data, can sometimes help the network's optimization algorithms find that valley, that local minima, significantly faster during training.
So what does this all mean? Let's check in with you, the listener, for a second. We've talked about a lot of intense architecture and calculus, but bring it all back to the core analogy of the source material, the biological human brain.
Right, connecting it back.
Your physical brain has roughly 86 billion neurons. But they aren't all firing at maximum electrical capacity all the time. If they did, you wouldn't be a super genius. You would be having a massive catastrophic seizure.
Your brain strictly regulates its own internal information flow.
It constantly dynamically decides which sensory signals are strong enough to pass on to your conscious awareness and which should be aggressively gated and ignored. Activation functions are exactly that biological mechanism translated to code. They are the artificial brain's way of regulating its own internal traffic, deciding which mathematical signals are vital enough to pass through the gates and which should be flatlined.
It is literally how the network achieves focus amidst the noise. And that concept of focusing on what is important, of cutting through the noise, is the absolute perfect transition to our next major architectural lead. Because focusing on relevant features is the absolute key to seeing the world through convolutional neural networks, or CNNs.
The vision models.
We are now entering the specific, highly complex domain of computer vision. Everything we've discussed so far has been about handling data generally, but processing dense visual images requires a fundamentally different, specialized approach to architecture.
Right, because if you take the regular dense neural networks we just described, where every neuron connects to every other neuron and you feed them a photograph, they struggle terribly. And to understand why, we have to strip away our human intuition and remember exactly how computers see.
A computer does not look at a digital photograph and see a golden retriever playing in a sunny park. It has no concept of a dog or a park.
It sees numbers.
A computer sees a massive, terrifyingly large grid of raw numbers. Specifically, it sees a grid of individual pixel values, usually ranging from 0, which represents pitch black, up to 255, which represents pure saturated white. To a computer, a 4K image is just a giant, overwhelming spreadsheet of millions of numbers.
And if you take that high-resolution image and just unroll all those millions of pixels into one giant, flat, single-file line of numbers and feed it into a regular, dense neural network.
Two things happen. First, the number of weights required to connect all those pixels explodes into the billions, making it impossible to compute.
And second, it loses the shape.
Exactly. The network instantly loses all the critical spatial relationships. By flattening the image, it completely forgets that a pixel representing a dog's eye is located right next to a pixel representing the bridge of a nose. It loses the geometry of the real world.
This specific failure of dense networks is exactly where the convolutional neural network, the CNN, was invented to save the day. A CNN is a specialized, highly structured architecture specifically designed from the ground up to preserve the 2D and 3D spatial structure of an image as it processes it.
It doesn't flatten the world. It respects the grid. And it tackles this monumental problem by dividing its processing into two very distinct phases. The first and most crucial phase is convolutional preprocessing.
This phase is mathematically beautiful. Instead of forcing the network to look at the whole massive, overwhelming image all at once, the CNN takes a tiny little square matrix called a filter or a kernel and systematically slides it across the image, pixel by pixel, row by row.
It's like a magnifying glass.
It's looking at the image through a tiny peephole, breaking the massive picture down into tiny, overlapping, localized segments. It's specifically hunting for microfeatures, a vertical edge here, a horizontal curve there, a sudden change in color contrast. And within this sliding phase, it utilizes a brilliant data compression technique introduced in our text called max pooling.
Max pooling is absolutely essential for computational efficiency. As that little filter slides over and looks at a specific 2x2 or 3x3 segment of pixels, it doesn't bother keeping all the numbers it finds. It executes a ruthless command.
It throws data away.
It isolates and extracts only the single highest pixel value in that specific microsegment, throwing the rest away. The core assumption driving this is that the highest numerical values represent the sharpest edges, the brightest spots, the most defining structural features of that specific area.
It aggressively throws away the redundant, boring, uniform background pixels like a massive stretch of blue sky and keeps only the high signal data.
It fundamentally narrows down a massive, computationally overwhelming image to find the tiny, specific, distinct details that actually matter to identifying the underlying object.
Yeah.
It shrinks the sheer volume of data exponentially while miraculously preserving the core geometric features.
Once it has done that exhaustive sliding, filtering, and pooling over the whole image, we transition into the second phase standard NN processing. The CNN has essentially functioned as a feature extractor. It has created a condensed, highly concentrated, abstract map of the most important visual features.
Then it passes the baton.
It takes that refined feature map, flattens it, and finally feeds it into the exact same kind of standard, dense neural network we discussed earlier to make the ultimate classification prediction. The CNN acts as an incredibly smart spatial filter for the regular network.
Let's ground all this theory with the concrete, real-world example provided in the source session, working with the Fashion MST dataset. For anyone entering this field, Fashion MST is a very famous foundational benchmark in deep learning.
It's a classic.
In the specific session outlined in the text, a CNN was built and trained to accurately classify 10 different types of clothing categories, things like t-shirts, sneakers, dresses, and ankle boots. And it was trained using a sprawling data set of 60,000 distinct training images.
Think about the actual scale of that task for a second. 60,000 images. The computer has to mathematically figure out the incredibly subtle difference between the shape of a sneaker and the shape of an ankle boot, entirely on its own, based purely on shifting grids of numbers from 0 to 255.
It's a heavy lift.
To make this computationally feasible, the developers in the text used a crucial pre-processing step called normalization. We mentioned that pixel values natively range from 0 to 255. Well, feeding dense numbers ranging up to 255 into activation functions can cause the network's math to get clunky, unstable, and slow to train.
So we shrink them.
Developers apply a simple mathematical fix. They divide every single pixel value in every single image by 255. The math is beautifully simple. 0 divided by 255 stays 0. 255 divided by 255 becomes exactly 1. A middle gray value of 127 becomes 0.5.
Normalization systematically shrinks all the pixel values into a neat, tiny standardized range, strictly between 0 and 1.
It doesn't change the image visually, the ratios are identical, but it makes the internal calculus drastically easier, more stable, and faster for the network's optimizer to process.
If we connect this to the bigger picture of deploying these massive models in the real world, we have to confront the single greatest danger that AI developers face: the threat of overfitting.
Overfitting is the absolute bane of deep learning.
It really is. It happens when your model trains too well, too closely on your specific limited dataset, instead of actually learning the underlying generalizable abstract patterns of what makes a shoe, the concept of a sole, or laces the network uses its millions of parameters to simply memorize the specific 60,000 training images perfectly.
It just memorizes them.
It memorizes the exact specific pixel placements, including all the completely random, irrelevant background noise, camera artifacts, or specific lighting conditions of the training set. The end result is a terrifying illusion of success.
It performs at 100% accuracy on the data it was trained on.
But the very moment you release it into the wild and show it a new, unseen picture of a shoe from a slightly different angle, it fails completely. It memorized the textbook flawlessly, but it never actually learned the underlying concepts.
It's exactly like a student who memorizes the answers to a practice test based on a smudge on the flashcard, but fails the actual exam because the questions are worded slightly differently and the smudge isn't there. So, how do we stop the network from cheating the tests like this?
The training session used an incredibly clever, almost counterintuitive architectural solution: the dropout layer.
I love the dropout layer.
During the actual training loop, a dropout layer acts like a chaotic, disruptive teacher in the classroom. On every single forward pass, it literally randomly turns off a certain percentage of the artificial neurons in the hidden layers. In the session text, they set it to 20%.
So 20% of the neurons just shut down.
Suddenly, they go completely dark and their weights are ignored. The network is violently forced to make its guess without being able to rely on those specific, comfortable neural pathways.
Why do that? Why break it on purpose?
It forces absolute robustness. It breaks dependency. If the network was lazily relying on one specific, highly active neuron that had just memorized a useless piece of background noise to identify a sneaker, suddenly that neuron is turned off.
The network panics.
Mathematically panics, yes. It realizes, I can't rely on that one single pixel anomaly anymore. I have to actually distribute my learning and look at the broader general shape of the laces and the curvature of the sole.
By randomly dropping neurons out in every single batch, you entirely prevent the network from becoming overly reliant on any single brittle pathway. You force it to build redundancy. You force it to learn true, distributed, robust patterns, rather than just memorizing localized, specific noise.
That's such a brilliant concept. You intentionally cripple and sabotage the network during its training phase so that it becomes exponentially stronger and more resilient when it faces the unpredictable real world.
All right, we have covered a massive amount of conceptual ground. We've covered the history of the friction, the biological inspiration of the architecture, the deep calculus of the learning loop, the vital gating of activation functions, and the specific spatial wizardry of CNNs.
Now let's bring it all down to earth. Let's look at Section 7, putting it into practice. Because all this high-level theory is fascinating, but how does a human being actually sit down and build this architecture today?
The source outlines a very clear, step-by-step developable recipe for writing this in code, specifically using Python and a wildly popular open-source library called TensorFlow.
TensorFlow, originally developed by Google, has become the absolute industry standard tool because it seamlessly handles all of the complex, underlying, terrifying calculus of backpropagation in the background so developers don't have to write the math from scratch.
The recipe for building a model is remarkably straightforward and modular once you understand the core concepts we've just discussed. Step 1 of the recipe: define architecture.
This is where you write the few lines of code to instantiate your input layer, declare exactly how many hidden layers you want, specify how many hundreds of neurons live in each of those layers, and define your output layer, specifically assigning your activation functions.
Like dropping a real U into the hidden layers and a sigmoid or softmax at the end. Step 2 of the recipe: set the optimizer. Remember the backpropagation we discussed? How the network meticulously adjusts its weights to find the bottom of the valley.
The optimizer is the specific, hard-coded algorithm that manages that entire descent process. The text prominently mentions the Atom optimizer, which is incredibly common right now. Think of Atom as a very smart, highly adaptive GPS that helps the model navigate down that complex error valley to the local minima as efficiently as mathematically possible.
It doesn't just use a static learning rate, does it?
No, it dynamically, automatically adjusts the learning rate for every single weight as it goes, slowing down when the terrain gets steep. Step 3. Set the loss function.
This is telling the model exactly how it should calculate its mistakes. You tell it to use mean squared error for continuous numbers, or, as the text specifically suggests for the fashion MIS classification problem, something called sparse categorical cross entropy. You are just explicitly picking the mathematical ruler it must use to measure its own failure.
Step 4 is to fit the model. This is where theory becomes reality. This is where you actually press start on the engine and begin the compute-heavy process. You feed your prepared data set, like the 60,000 normalized clothing images, into the architecture you built. You explicitly set the number of epochs to define how many times it will see all the data, and you dictate your batch size to manage your computer's memory. The exhaustive training loop finally begins.
And finally, step 5, evaluate and verify. Once the grueling training is done, you absolutely must test the model on completely unseen data, a test set that was strictly quarantined from the model during training.
What you are desperately hoping to see on your screen is the loss metric going down and the accuracy metric staying consistently high on that unseen data.
If accuracy is high on data it has never encountered before, you know you have successfully avoided the overfitting trap and built a genuinely intelligent, generalizable model. It's a clean, logical, incredibly satisfying recipe. And the text offers a really crucial pro tip for anyone actually trying to run this code: the importance of the seed value.
Oh, the seed value is critical.
We mentioned earlier that when a neural network is first initialized, its starting weights are assigned completely randomly. This introduces a chaotic variable. It means if you run your beautifully written code today and I run the exact same code on my computer tomorrow, we might end up with slightly different final accuracy results simply because our model started from different random starting lines on the mountain.
To fix this frustrating variance, developers use a seed value. It's just a specific arbitrary number you plug in at the very top of your script that forces the computer's random number generator to generate the exact same mathematical sequence of random numbers every single time the script runs.
It ensures total scientific reproducibility. If you share your breakthrough code with a researcher across the globe, the seed guarantees their model will start at the exact same point and get the exact same final results you did.
This raises an important question, though, and it brings us to what might be the most profound, landscape-altering practical point in the entire source text. We just walked through the step-by-step TensorFlow recipe. But the day-to-day reality of modern software development is shifting so rapidly it's hard to track. The text explicitly notes that you, the listener, or any aspiring machine learning engineer, no longer need to painstakingly memorize every single line of TensorFlow syntax.
You don't need to spend hours on forums trying to remember where every comma, bracket, and specific function call goes,
Yeah.
because we now have AI tools, large language models like ChatGPT, that can literally write the boilerplate structural code for you in seconds.
It's incredible.
You can just open a prompt and type, write a Python TensorFlow script for the fashion MES dataset using a convolutional neural network with max pooling, the atom optimizer, and include a 20% dropout layer to prevent overfitting. And boom, flawless executable code appears on your screen. The friction of coding has vanished.
If the machine is now capable of writing the highly complex code required to build the machine, what exactly is the human supposed to be doing? The text answers this emphatically, and it's a critical mindset shift. The human's job has evolved away from memorizing syntax and typing out code, and has shifted entirely toward deeply understanding the high-level intuition behind what the code is attempting to achieve.
ChatGPT can instantly write the code, but ChatGPT cannot intuitively tell you why your specific model is currently overfitting on your unique proprietary company data.
It cannot tell you if a 20% dropout is better than a 50% dropout for your specific edge case. It cannot tell you if you've chosen the right activation function to capture the bizarre nuance of your unique dataset. The human engineer is no longer a bricklayer. They are now an architect of intuition.
You desperately need to deeply understand the structural concepts we've discussed today, the forward pass, the topology of error landscapes, the gating mechanism of activation functions so that you can debug, guide, structure, and optimize the systems that the AI is merely helping you type out. It is a complete paradigm shift in what it means to be an engineer.
We are moving from being the people mixing the physical mortar to being the city planners designing the flow of traffic. The value is no longer in the typing. It's in the understanding of the architecture.
That is the perfect summary of the current state of the art. Well, we have covered an absolutely incredible amount of ground today. We started by picturing those medieval castle guards clapping on stone walls out of a primal desire for communication convenience, and we traced that exact same human impulse all the way through the brittle, frustrating limitations of manual, rigid machine learning rules, straight into the data-hungry black box world of modern deep learning.
We've meticulously mapped out the artificial brain, exploring how hidden layers, weights, and biases process abstract information.
We waded deep into the calculus of the learning loop, understanding how models make their sequential guesses, measure their catastrophic errors using mean squared error, and run complex backpropagation to slowly fix their mistakes and navigate the lost landscape.
We've seen how activation functions act as vital, mathematically necessary traffic gates to introduce nonlinearity, and how convolutional neural network can utilize the brilliance of max pooling and chaotic dropout layers.
To finally allow computers to actually see and generalize complex visual images like the fashion MES dataset without just memorizing the noise. And finally, we saw how tools like TensorFlow and now the advent of code writing AI have permanently transformed the human developer's role from a code memorizer into a high-level master of architectural intuition. You've gone from the stone castle wall to the bleeding absolute edge of modern AI architecture.
It is a genuinely remarkable technological journey to trace. But before we sign off, I want to leave you with a final thought to mull over, building directly on that last critical point about the shifting nature of intuition. We just firmly established that AI tools are already highly capable of writing the structural code for deep learning models.
Right.
And we know that deep learning models themselves are specifically inherently designed to figure out their own complex, nonlinear rules without human interference. That is the entire point of accepting the black box.
Right.
So the human is currently left sitting at the top, providing the high-level architectural intuition. But extrapolate that out. How long until the AI develops its own architectural intuition?
Wow.
If we continue to feed these systems exponentially more raw data, allowing them to optimize their own code and mathematically define their own error landscapes, will we eventually reach a tipping point where AI is designing fundamentally new neural architectures entirely on its own? Architectures that don't clumsily mimic the biological human brain at all, but rather something entirely alien, operating on dimensions of high-dimensional logic that we couldn't possibly comprehend or audit even if we tried. It is the ultimate, inevitable extension of our original desire, completely removing human interference in the pursuit of absolute convenience. Something for you to think about.